Xohlasangiz gapirishingiz mumkin. Tushuntirib, Ollabek keyin уже
Zapisni boshladingiz-da уже?
sinapani
Ha, okey.
zapis qanday ko'rinadi, qanday qilinadi. Sizda o'zgaryaptimi nimalar? Fonlar? Sizda bir xil turibdi-ya?
Ha?
Ha, qarang, hozir men bir narsa o'zgartiryapman. Mana o'zgartirdim. O'zgartirib, sizga hech narsa o'zgarmayaptimi o'shanda ko'rdingiz sizda? Bo'ldi, tushundim.
Assalomu alaykum. Daniel? Daniel eshitilyaptimi?
Assalomu alaykum. Ovozimiz yaxshi eshitilyaptimi?
Juda ham yaxshi eshitilyapti.
Ha, tushunarli, rahmat.
Tushunibdimi?
Hello.
Welcome. Hello, welcome, Professor Tabatai. Nice to see you again.
Nice to see you.
Hello.
Hello, Rostam. How are you doing?
Good. Okay. So far we have Jizak Political University, right? Institute.
Yeah, Jizak Polytechnical Institute.
Also, Nawai branch, Nukus branch of Nawai Mining Institute. We are looking for still for Karakalpak State University. Danyar Barslarma. Oh, we still have 2 minutes.
Okay.
Okay. Okay. Now the key, do you hear us? Istvatslarma?
Assalomu alaykum ağa. Siz yaxshi eshitdingizmi bizni?
Okay. So
Hozir Zanira ağa keladi hozir.
we still have 1 minute left. Actually, Dean called me right now. They have some problems with connecting, but in a few minutes, maybe they will join us. So maybe we begin.
Yeah, I think it's a good idea.
Okay. Dear friends, dear colleagues, it's my pleasure to introduce
Or go ahead.
Okay, so let me it's my pleasure to introduce Professor Tabatabai, Habib Tabatabai. He's a professor and a director of Structural Engineering Laboratory and Department of Civil and Environmental Engineering, University of Wisconsin, Milwaukee. Actually, this University of Wisconsin, Milwaukee is within a top of 1,000 of worldwide rating university. And actually, Professor Tabatabai, he is my mentor. I am proud of it. And just I can say, you may find any information about Professor Tabatabai. I can just mention just his H index is 38 and citations is would you believe me, in 1,677. So it's my pleasure to introduce Professor Tabatabai, and his topic today is new advancements and trends in civil engineering. Please, Dr. Tabatabai.
Thank you very much. I appreciate it. Salam alaikum to everybody. I think you have to allow me to share. Right now it's disabled. Professor Abdulnazarov.
Jamshid.
Okay, now it's, thank you.
Yes, you have now. Please check.
Okay. Okay, thanks again. Thank you very much. It's a pleasure and honor to be joining you today and talking to you about new advancements and trends in civil engineering. I had the pleasure of meeting Professor Shnazov and Professor Abdulnazarov a few months ago, and I'm honored to get to know them, and they have helped me understand a lot more about Uzbekistan. I'm grateful for that. Some of the topics that I'm going to talk about is very broad. We are going to talk about some of the new things that our civil engineers, at least in the United States, are looking at in terms of the future. So we have a changing world. We have a lot of challenges that are facing the world, and we as civil engineers are in forefront of trying to solve those issues. Those are some of the major issues, but in every aspect of it, civil engineers have a lot to do. They can guide and shape the whatever solutions that we found for our generation and for future generations as well. So in terms of our challenges, by the way, my background is a lot more in bridge engineering. So I show a little bit more pictures of bridges, and I'll try to explain them. This is a bridge in the Alps in Europe. And so some of our challenges, main challenges involved first and foremost climate change and the effect that it will have on all aspects of civil engineering, environmental degradation, issues associated with development and the environmental problems that would cause, natural hazards, windstorms, earthquakes, in case of windstorms, floods, windstorms and floods are aggravated by the issues of climate change. We also have limited resources. In the United States, there are a large number of bridges that need to be repaired, but they have to be prioritized to be able to handle all of them and on a critical basis. So we have limited resources and we have to work with those limited resources. Also, there are limited energy sources, and some of the construction materials that we use have a lot of embedded embodied energy. That means it takes a lot of energy to produce them, and we want to minimize those energy levels in the materials. We also have an issue of some of the high quality construction materials, for example, aggregates that are used in concrete. We find them less and less high quality materials, and we have to work with lower quality construction materials as well. So these are all challenges that we have to deal with and we have to solve. So the approach that people in civil engineering have taken is to focus on a number of things in the hope of making a difference in addressing those challenges. One, first and foremost, is sustainability, and I'll explain that a little bit more in the next slide. The other is resilience. We have to have structures that are able to sustain forces of nature, but first and foremost, they have to preserve human life. So in earthquakes, we want to preserve human life to the extent possible, and also try to minimize damage. So after an earthquake, there is opportunity for the structure to be occupied again and the life to resume its normal process. We also are looking at advanced materials, new materials that are going to give us higher strength, lower degradation potential, and longer service life. We also look at new design methods to make our design of infrastructure systems, our structures, to be compatible with our goals. And of course, new construction processes to minimize waste, to minimize impact on people's lives, and advance development. Let's talk about sustainability a little bit. And that we define it as economic development and societal advancement that minimizes resource and energy utilization. We want to minimize energy utilization. We want to extend the service life of structures, and we want to limit environmental degradation, not only for the benefit of our generation, but for future generations as well, and to preserve our quality of life worldwide. Now, the picture you see on the left is the Great Stone Arch Bridge in China. That was built about 1,400 years ago, and it was one of the first major bridges that the arch was not semicircular and it was flattened. And that was a great achievement for its time to be able to do that, and is still standing to this day. Sustainability, and some of the pictures here, by the way, point to Gard in Aqueduct in France from 19 BC. So over 2,000 years ago, it was built for transporting water, and is still standing. I always like the Khaju Bridge in Esfahan, Iran, which is not only serve the function of a bridge transporting people across the river, Zayan Darud River, but also it was a work of art, so that it also nurtures human beings in terms of the art that it produces. So coming back to sustainability, sustainability means enhancing durability, extending service life of a structure. We want the structures to have a longer service life. We want to reduce carbon footprint. We want to use ideally a carbon neutral system developed with the climate change that we have currently. We want to limit energy usage, and we want to limit embodied energy in our construction materials. We want to beneficially use byproducts, waste materials from industrial processes into construction. So not only to use a waste material, but also to improve the properties of construction material. And finally, we want to preserve and not harm the environment. Now, concrete is the most used construction material in the world. And of course, a major ingredient of concrete is Portland cement, and it's produced all over the world. Portland cement is a significant contributor to CO2 emissions worldwide, about approximately 1 kilogram of CO2 for every kilogram of cement is produced. That's generally roughly about 8 to 10% of global CO2 emissions. It has a lot of embodied energy because a lot of energy goes into producing Portland cement, the clinker, the high heat that there has to be applied, and that builds in the significant energy into the material. Now, what can we do about it? We have to work with concrete. It's a major construction material, but we can try to reduce the impact of it on the environment by using materials that mimic, that act like cement, but they are not cement. And they are ideally could be waste materials that we can use in there. And those we call pozzolanic materials, and I'll explain why the word pozzolanic. Those can not only reduce the Portland cement usage in concrete, but also can improve the properties of concrete and make it more durable. Pozzolanic materials, by the way, pozzolanic comes from the old Roman word pozzolana, which was a volcanic ash. And pozzolanic material is a material, typically very fine powders, that become cementitious in the presence of lime. Okay, so it can be used to replace part of Portland cement in concrete. 10%, 15%, 20%, 25% can be reduced with that. So what are some of the major pozzolanic materials? For example, fly ash in coal burning power plants, when in the stacks, they put devices to catch the fly ash from getting out into the atmosphere. And in the United States, for example, about 100 million tons of ash gets produced. For many years, they would be landfilled, but then research showed that they could be used in concrete and replace the cement in concrete. This pozzolan, because Portland cement has lime in it, so it would react with that and acts as a cement and reduces the impact of cement, but also improves proper durability properties of concrete. So the picture you see in the middle is pictures of fly ash, this is on a scanning electron microscope and the micron range. So you will see very small spherical particles. You also have silica fume or microsilica. It's a very good pozzolan that is obtained from production of silicon in electronic industries. It's a waste material that converted to very high valuable material for use as a cement replacement. Ground granulated blast furnace slag is also made from a waste from a iron and steel making industries. Also around the world, wood ash, for example, rice husk ash, volcanic ash, these all can become cementitious in the presence of lime. Other materials, metakaolin, calcined clay. We are working at the University of Wisconsin, Milwaukee on developing new pozzolans based on industrial waste materials that we can be beneficial to the usage, reduction of cement use. In terms of durability, we know structures that have withstood the test of time, centuries in service. The stone arch bridges throughout Asia and Roman Empire are indicative of that ability to make durable structures. Now, the Roman arches were typically semicircular arches, but we'll see with the Great Stone Arch Bridge, they became more flattened over time to become more efficient. However, how can we make concrete more durable? There are ways that we can make concrete more durable, extended service life. One is to use what we call high performance concrete, which is essentially reduces permeability. A major way that concrete is harmed in long term is when water mixed in with harmful chemicals like chlorides get into the concrete, sulfates, for example, get into the concrete, and if there are embedded steel reinforcing bars, causes corrosion of the steel, and when the corrosion happens, the steel wants to expand. As it expands, pushes the concrete away, cracks it, and leads to spalling. One thing that would help a lot, especially in the United States, in cold regions like in Wisconsin, and that I am in, in order to, in the winter time with ice, to allow cars to go on the roads, they add a lot of salt to the roads. That it's chlorides, and that is very harmful, causes a lot of damage. One way that you can mitigate that and reduce its effect is applying sealers and coatings, but you have to do it early before chlorides get in, and you have to repeat the process every few years. This adds to the cost, but it will extend the service life of the structure. And people here in the United States starting to realize the importance of prevention. An ounce of prevention is better than a pound of cure. That means slight efforts in preventing corrosion or deterioration can extend the life of the structure quite a bit. Another factor that leads to premature durability problems is insufficient cover for the steel reinforcement that is close to the surface of the concrete. Also, using good quality ingredients, proper placement, these are all very important in durability of concrete. In steel, when steel structures, when they're exposed to the environment, they have to have regular painting. Otherwise, there is a type of steel that's called weathering steel, and that would oxidize in the appropriate environment, and that creates a hard surface that prevents additional corrosion to take place. There's also other types of corrosion resistant steel. But most important thing, simple things, is controlling water runoff. When the water, rain or other water sources on a bridge or in a building, if they are not controlled and get into where they're not supposed to be, that causes a lot of damage. Now, we look at recycled materials or waste materials in two ways in concrete. One, concrete itself can be reused when it's end of its service life. When we have concrete pavements, it is very common in the United States to break it into aggregates and use it as sub-base material. Okay, so you are reusing the material into another roadway. Now, there is research going on to use that in concrete as well. That's a little bit more challenging, but it has been successful in some research projects that have been done. Another way is to put waste materials, which is pozzolans, for example, into concrete. The bottom picture here shows this is a scanning electron microscope. You see the fly ash inside the concrete. That fly ash helps a lot with as a pozzolan, helps a lot with the durability of concrete. Now we recycle pretty much everywhere, if there is asphalt pavement, when they want to remove it, they recycle the material. The bitumen and the aggregates, they're all recycled. In the US, a lot of houses have asphalt shingles. Those asphalt shingles are also recycled. Now, I'm going to talk a little bit about resilience now. That's another important topic in civil engineering. We refine resilience as the ability to sustain and resist the force of nature and recover from them, forces of nature being earthquakes, floods, winds, and recover from them without loss of life. That's the first and foremost thing, no loss of life. So even on the most severe earthquake, we want to preserve life. Our structures should not collapse, okay? However, we expect some level of damage because to make it without damage, it's going to be very costly. But more and more people want to be able to have usable buildings right after a major earthquake. So that makes our job more difficult to not only preserve life, but also preserve the structure as well, okay? So resilience is to, after you're hit, stand up and continue again. That ability is very important in structural system. The picture on the right is the Brooklyn Bridge. It's the Brooklyn Bridge in New York, and that's an example of a resilient structure. It's been there for a long time. So resilience, avoiding loss of life under the most severe forces, avoiding structural collapse. Now, a lot of times we do that by making the structure redundant. That means we don't rely on the structure to have one line of load path to the foundation. We want multiple loads. So if one gets damaged and severed, the others keep the load transferred to the foundation. You don't want cases where failure of one element causes the failure of the entire structure. We can't allow that. Okay, so but more and more, let's say in Los Angeles, if a major earthquake happens, people have been saved, but the more and more want to reduce damage. We want, for example, the hospitals to be operating fully. They cannot be shut down. So we designed those to a different standard. It's going to cost more, but we want about emergency vehicles, emergency centers, hospitals, police forces. They have to be able to operate in the worst condition. So they have to be designed for a different level of performance after an earthquake. So let's talk a little bit some of the advanced materials that are being worked on now. Those pushing for higher strengths, pushing for lower degradation, pushing for lower environmental impact and lower embodied energy. So some of the advanced civil engineering materials, by the way, the picture on the right is Akashi Kaiko Bridge in Japan. It's the longest span bridge in the world. It has been there for many years. It's a suspension bridge between two islands in Japan with a main span. The distance between the towers that you see in those two towers, the distance between them is 1,989 meters. So we're looking at some advanced concrete materials, advanced steel materials, fiber and reinforced polymer composites that are finding more and more uses in civil engineering. Advanced wood or timber materials. That's something new with a new development recently. You get a lot of activity in timber materials, wood materials. Advanced asphalt materials, self-healing materials, shape memory alloys. Shape memory alloys are materials that if you deform them and if you apply temperature, they get the original shape, and it can be used for that property can use for many purposes. So I'm going to touch on some of those in the next slides, not all of them, but so why do we want advanced concrete materials? We want to reduce the carbon footprint of concrete. We want to improve durability and enhance service life of structures. We want to improve strength, both compressive and tensile strength. We know concrete is relatively weak in tension than it is in compression. We want to address the dwindling supply of quality aggregates for concrete, and we need to find new ways to recycle old concrete. So these are all motivations to do new research, to find new materials. One of the most active research areas in concrete in the United States is ultra high performance concrete. And this is very high strength concrete that I'm going to talk a little bit more about later. We also have older fiber reinforced concrete that it has properties that improve concrete. However, a typical fiber reinforced concrete, the fibers cannot replace the structural concrete. They cannot replace the steel reinforcement. We have a Professor Sobolev at our university that is a world expert on super hydrophobic concrete, where using nanomaterials, you make the surface, as I said, durability comes in when water penetrates into concrete. By making water moving away, you improve the durability of concrete, and that's super hydrophobic concrete. There are works that are being done on self-healing concrete. So if a crack develops, automatically it can work to fill that crack back up. There are different ways of doing that, and research is being done on that. Also, there is self-cleaning concrete, especially for important architectural features. You don't want the dirt and dirt to cling to concrete surface. So by adding, for example, titanium dioxide, you can make photocatalytic concrete that would move. It's easier for the dirt to wash out and not dirty up the surface of the concrete. Now let's talk a little bit about ultra high performance concrete. The Federal Highway Administration, there are different definitions for it, but the Federal Highway Administration in the US defines UHPC as concrete at least 150 MPa in compressive strength. Now, it also has to have high tensile strength, but not the fact that if you get to a tensile strength, we don't want the strength to drop to zero. We want it to sustain itself. So after cracking, it should still hold a 5 MPa tensile capacity. That means it will give it a more ductile behavior of for concrete. Normal concrete, when it gets to a cracking load, suddenly drops to zero, and that's very brittle nature. So this will address that. Of course, you will use steel reinforcement in UHPC as well to provide additional strength. Now, one thing typically with UHPC, water to cement ratio is less than 0.25. If you have worked with concrete, you usually work with higher numbers. So this will make it very difficult to work with it. That's why you have to use chemicals, specifically super plasticizers, to make it flowable so you can place it correctly. This has also high steel fiber reinforcement. Now, these are not bars, these are little steel needles. Some of them have bent ends so that it's mixed in concrete. And that is what it gives you, that additional tensile strength post cracking, but it makes it more difficult to mix it. Okay, there is special attention to aggregates. There's no coarse aggregate used or gravel used, only fine and very fine materials. Pozzolanic materials are used in there. Small granular materials used there. As I mentioned, chemicals such as superplasticizer are used there so that you get high flowability of concrete. Now, in the top picture, you see the first UHPC bridge built in the US and Iowa, USA. And then, but the most application of UHPC now in the US is in accelerated bridge construction, which I'm going to discuss later. We want to make the structures modular, make them at a factory or somewhere else, bring them and put them together very quickly. That way we reduce the impact on people in terms of transportation. We want to minimize downtime. So these are precast, brought in, but there are joints between them. The big problem with having these modular units is with earthquakes and with potential movement and cracking that happen with other forces and creeps and shrinkage and temperature effect. But we use UHPC at the joints between them to make them a solid structure. By the way, this picture is the longest cable-stayed bridge in the world that's in Russia. So in terms of advanced steel materials, there are some developments regarding steel reinforcing bars or rebars for concrete. And there are, for structural shapes of steel, we have, of course, high strength, low alloy steels, corrosion resistant materials, stainless steel, and weathering steel that I talked about earlier. In terms of reinforcing bars, up until a few years ago, the most common one in the United States was a 60 KSI or 414 MPa reinforcing bar. That's yield strength of the bar. Now they're commercially available to get 550 or almost 700 MPa bars for use in concrete. You also have stainless steel bars for corrosion resistant, but those are expensive. Yeah, there's galvanized bars, are not as effective as stainless steel, and they have issues with using alkali environment in concrete. Epoxy coated steel bars have been used a lot. They do help. However, if the quality is not good, if there are small what we call holidays or small holes in the epoxy, the corrosion that you could get is far worse than if you hadn't put the epoxy on it. It's a very important lesson that first applications of epoxy coated bars in the United States had major problems, and that was mitigated later. There is also fiber reinforced polymer or FRP composites that are used, and those are essentially these are fibers. Those are typically continuous fibers, either glass fiber, carbon fiber, aramid fiber, or basalt fiber, and there are others, mixed in with a polymer, an epoxy, and you can make bars with it. You can make sheets with it. There are two problems with that. One is a polymer is not fire resistant. So for indoor use in structures, there is a danger of fire and the damage to that material unless you protect it. But the second issue, more important issue, is that in steel, you have a very well-defined yield which prevents brittle fracture and premature failure. But in FRP bars, the stress strain curve is straight all the way to failure. So if when it reaches failure, there is a sudden brittle fracture of the material. However, it has its uses. For example, if you don't want magnetic, if you have a MRI unit in a hospital, for example, and you don't want the walls to have steel in them because you have a working with the magnet, you would reinforce them with these FRP bars. Another very good application is seismic retrofitting, improving the strength of whether it's columns, whether it's connections, whether walls, to apply these, you glue these things on the surface with carbon fiber, with glass fibers to improve the strength for earthquakes. They have many advantages, but as I said, the big disadvantages are brittleness and fire resistant. They also make them on the top right in sections, I-beams, channels, and so on. Now, in terms of wood materials, there has been a lot of activity recently on wood, and the way these are called cross-laminated timber, CLT, is produced in factories. You take the dimensional lumber and you put them in one direction together, and then you go the other way together, and you glue them together. You have a strong and good system in here that is more and more research is being done on it. And I read that there is a 80-meter tall tower under construction in Norway with CLT. So in terms of advanced design methods, we need architects working on more sustainable, efficient architectural systems. Structural engineers work on better structural design systems. This is a picture of architects. A lot of them like to make green roofs where vegetation on the roof, which has its own challenges, to improve the number of environmental issues. There are design methods now that our software for design are very advanced, including visualization. We're working with performance-based design, as I mentioned earlier, that when a client wants to be operating after an earthquake, depending on what performance they want and how much costly will become, then we can design according to that requirement. There are more advanced seismic resistance methods and devices. I'm not going to get into that matter. Also, energy and carbon consideration. Now, the picture on the right is a picture of a building that was proposed for Dubai, and is supposed to, each floor is supposed to be able to rotate 360 degrees. Now, I can imagine that it creates a lot of design challenges, and maybe that's why it hasn't yet been built, but it was planned to be built a few years ago and still talks about it, but it hasn't been built yet. Now, touching a little bit on the advanced construction materials, or construction methods, essentially, we want to reduce construction impact on people's lives. We want to reduce the construction time and improve efficiency. So there are modular construction ideas that I talked about. There is building information modeling that I'm going to talk a little bit about, BIM or building information modeling. 3D printing of concrete structures is a very active research now in the United States, and I'll explain a little bit more. Accelerated bridge construction relates to modular construction, but again, you want to build pieces of bridges not on site. You want to build it somewhere else in a short time bring it on the bridge site and put it together, make the bridge, so you are not disturbing people's lives and traffic as a result of that. More developmental construction robots that do construction, drones, the use of drones is now very widespread in inspection of bridges, and also more recently in artificial intelligence and machine learning applications in civil engineering. So in terms of 3D printing, it's a process where you are putting layers of concrete as you do 3D printing. And this is a lot of issues with that still, but there's a lot of research being done on that to try to, then you can create any shape that you want with this process, with this robot. So in terms of building information modeling, this is a process that you have different tools to represent the structure in digital form. It helps greatly with visualization down to pipes and everything else in the structure, and allows the architect, the engineer, the contractor, everybody working together. If a architect changes part of the design, the structural engineers' drawings would change accordingly, or the models would change accordingly. So it has not only geometry, it has data, and you can zoom in and see if there are conflicts and so on. So this is a very active, has been very active, and it's widely used now in construction in the United States. As I mentioned, accelerated bridge construction, where the motivation is improve quality and reduce impact on people. You don't have to close roads. You don't have to for a long time. And so you build the pieces and you bring them, and there are connections. The issue would be the connections, and a lot of times we use UHPC in those connections. This bridge is, when I was younger working on this bridge, had a problem, and we were investigating that problem, and it's in Mobile Bay, Alabama. So in terms of concluding this, there is a great need for sustainable and resilient structures today to face the challenges that we face in the world today. We want to have new technologies develop, new materials to face that challenge. Your modern civil engineering structures and systems and infrastructure have to be efficient and durable, with low embodied energy and minimum impact on the environment. Now I finish with this picture of a Hone Bridge in Milwaukee. Professor Ishnazov and Professor Abdunazarov are familiar with this structure. This is very close to where they are right now. And this is a magnificent bridge, almost collapsed in about 20 years ago due to brittle fracture of steel, but fortunately it did not. So with that, I conclude my remarks. I appreciate your attention and thank you very much.
Thank you so much, Professor Tabatabai, for such an interesting lecture. So, dear friends, dear colleagues, if you have some questions or discussions about lecturing, okay, let me actually ask a question. Professor Tabatabai, I can do it, of course, tomorrow in our class, but okay. During the, do you have some researches on salt resistance? Because, you know, it's big issue for our region, especially for Karakal, Pakistan, because we have a very salty underground water as well as ground, or the soil itself, soil. So do you have some kind of research at UWM on salt resistance of a concrete? Or
Yes.
actually tell us about I know a lot of guys who is carrying out the research under your guidance, so maybe you may told about your lab also, researchers you carried out.
Yeah,
Thank
so thank you for that question. Yeah, in terms of salt, we did a number of research projects for the related to corrosion resistance and salt mitigation, and especially for bridges. And there are several ways to address that. One is to getting the salt water away from concrete, especially reinforced concrete. Now, how do we do that? By making concrete less permeable. That means not allowing fluids to get in. How do we do that? A very simple way would be, or a very straightforward way would be to increase strength, because as the strength increases, compressive strength increases, permeability gets reduced. But it's not just strength. With the use of fine pozzolanic materials blocks the path for fluids to get into concrete, and that helps with mitigating salt coming in. And that helps also, as I mentioned, a major thing that it has an initial additional cost, but long term it helps the service life of the structure, is to apply sealers and perhaps coatings. Since there's a slight difference, sealers penetrate into concrete, coatings protect by staying near the surface. If you apply them early, before salts get in, they are very effective, but you have to reapply them every few years. So that needs a discipline and a maintenance cost to protect these things down the road. But if salts get in and get to the level of reinforcing steel, whatever you put on top is not going to do much more. It is going to continue the deterioration rapidly. We are doing some research. We are actually starting a research project at the laboratory, structural laboratory, for the Wisconsin Department of Transportation on using concrete overlays over bridge decks to interpret with respect to protecting the bridge itself. And we've done several studies on repair of structures along those lines as well in that lab. Thank you.
Thank you. So, dear colleagues, if you have some questions to...
Assalomu alaykum Rustam.
Da. Wa alaykum salam.
Ko'rishganimizda juda quvonchliman. Jamshid Abduzar o'z oldidan rahmat. Hozir bu yerda Navoiy Qanchilik institutining Nukus filialining studentlari, professor o'qituvchilari qatnashib o'tiribdi. Men qasimda kafedra boshlig'i, fakultet dekanlari, direktor o'rinbosarlar, studentlar qatnashib o'tiribdi. Bugungi uchrashuvni shu ko'rinishtirganingizga rahmat. Jamshid, sizga ulkan rahmat. Siz bilan ko'rishganimizga juda quvonchliman. Studentlarimizning bir savollari bor ekan, ruxsat bersangiz so'rovlar.
First of all, good morning. And I have a question. We know natural disasters like earthquake, floods, but all the causes of these are using materials and excavating fossil fuels. So what's the solution of avoiding it?
I'm not quite sure I got the question. So in terms of fossil fuels, we're talking about?
Yes.
Yeah, in terms of substituting something else for fossil fuels, right? Yeah, that falls a little bit outside of my area of expertise, but in general, the approach that is taken here is moving towards renewable energy sources and away from fossil fuels. I don't think it can happen very quickly, but if I understand the question, so there is movement in that regard, moving away from fossil fuels in transportation, in other areas for power plants and so on. But it is going to be a long process in moving away from that. I hope I understood your question correctly.
Are you satisfied? Okay.
If you
Thank
don't
you.
mind, excuse me, if you don't mind, could you please stop your screen and share your screen, please? Because it's a
Yeah.
recording, yeah, it will be more comfortable
Yeah.
for other participants.
Sure, let me, you can somehow, I don't have that here. Can you undo the somehow?
Okay, let me try.
Good morning. Let me ask some your question. My name is Murat Superbayev. What kinds of global solutions have been action or have been discovering to keep our environment safe to next generation?
Thank you for that question. In terms of the environmental impact of what as civil engineers we are doing is the use of concrete. I think one, at least within my expertise, the widespread use of white concrete and Portland cement in terms of global impact, that's the biggest impact that there is in terms of the total CO2 emissions that occur. But in terms of other environmental degradation that is significant throughout the world, civil engineers have a big responsibility to big role to play in this. And from now Uzbekistan probably won't have that issue, but in terms of a lot of big issues related to rising water levels in coastal cities where flooding will be a major event, and to try to solve that, it's going to be a big problem. Environmental issues in terms of pollution, air pollution, industrial pollution, these are all big challenges that have to be faced, and time unfortunately is running out. We have to act on those, and in all of those, the environmental engineer, at least in the US, as part of civil engineering, is a branch of civil engineering, and our department, of course. And there's a lot of work being done on water. One of the biggest research facilities on fresh water is in Milwaukee, and we're trying to preserve that resource from pollution, from contamination, and so on. So it is a big challenge. It's not an easy process, but it's something that has to be done. Unfortunately, with the determination and resolve to solve this problem. Thank you.
Thank you. Any other questions?
Yes.
Oh, yeah.
Yes.
Good morning. My name is Laminated, and I study Nukus branch of the Navajo State Mining Institute. You have just mentioned about using recycled materials, and I want to ask you about processes of reusing recycled materials.
Yeah, there is a wide range of recycled materials, but in the way in the US it's started is that when you see materials that are, for example, they're too much, that are being landfill, like I don't know if Uzbekistan relies on coal burning power plants, for example, but in the US, there were, and there are still a lot of coal burning power plants, and they were creating these gases escaping with a lot of solid materials, small solid materials. Then they controlled that by putting a filter, and they were collecting millions of tons of fly ash. Now with that, they had to put it somewhere. So they had to create landfill. They had to prepare material places to put that in there. So it was an immediate need to address that. So you have, the best approach would be to look at big issues, big materials that can be recycled, and find ways with research to effectively use them. Now it is very successful in terms of use of fly ash, that they go in the old landfills and remove the materials, because they can sell them at very high prices, become valuable. Something that was waste and not valuable, with research, it became valuable. And then when it becomes valuable, then it's going to be used continuously. So the strategy that works, I think, is start with in your area to see what are waste materials that are large and difficult to handle, and try to place research on those to find beneficial uses and make those usable and beneficial materials, whether it's in construction or whether it's in other applications. I hope I answered your question.
Thank you. Any other questions?
Yes.
Oh yeah, please.
Assalamu alaikum. Jiza Polytechnic Institute'da iştileptim Jamshid.
Ha, iştilepti bemalol.
Polytechnic Institute professor o'qituvchilari va talabalari ham mana bu Habib Tabaydi qiziqarli ma'ruzasi bilan tanishdik. Hozir talabalarimizda savollar bor edi. Shularni bersak marhamat.
Good morning, dear professor. Assalamu alaikum to our neighbors from other cities. So my name is Timur Sharipov. I'm a student of Jizak Polytechnical Institute. Professor, thank you for your lecture. I'm fully joining to all your words about the problem of environment. Even in our city, we can join with it. If you go 50 kilometers away from the city, you can see the land, kilometers of land, which look like covered with snow. But it's not snow, it's industrial trash after producing Portland cement. And it's a disaster of our region. And my question, what do you think, Professor, about 3D printers? Can they fully occupy construction of buildings and structure sphere? And please, can you share with your opinion about the fate of this sphere? Thank you.
Thank you. So first on the, again, it's there are environmental issues everywhere. It is, if there is that environmental issue, I think the universities are the places that can solve those, because the state of knowledge is at the university. So with small scale, you can start to find solutions. There are you can look at resources, other places have addressed this problem. So the engine for solving your environmental problems, structural engineering problems, civil engineering problems is the university. And through research that can be done. They're all capable people that can address problems of the society. In terms of 3D printing, one of our former students is a professor now at Princeton University that's leading a lot of research on 3D printing. And the big challenge there is, as you place the materials, what happens to reinforcement? So there is a lot of work being done, how we manage reinforcing steel in concrete. How do we manage creep and shrinkage of concrete, especially shrinkage at the corners? So there is still a lot of work being done, even though people have built units with it. There is still many research areas. That's why a lot of universities are putting emphasis on that. Potentially, when those problems are solved, potentially could revolutionize the construction of whether it's residential units or bigger commercial units. It could revolutionize those, but this is still in the development phase. And every day we see more interesting research coming out from different places. So I see in the future, probably not very distant future, it becomes a lot more practical. And it could, as I said, it's essentially a robotic construction. You build a house or a building with robots. And if you can do that and then make sure that it is capable of resisting seismic forces, for example, or wind forces, then it will, in my view, it will replace all the conventional ways of doing that.
Interesting.
Thank you.
Thank you.
Good morning. Good
Other
morning,
questions?
Mr.
Yeah,
Tabatay.
please.
Morning. Salam alaikum.
Salam alaikum. I would like to express our thanks to you, Mr. Tabatay. It's a very beneficial conference, and our students and our staff of Nukus branch of Nawai State Mining Institute take a lot of information from you, because our sphere and our professions belong to your sphere too. And our professor, Mr. Karamaddin, want to ask you to work together as a project. We have a lot of research. Do you know about Moynak? Have you heard about this region? Moynak, which is situated RLC. Have you heard about
I've heard
the
of RLC, yes.
And there are a lot of resources which helped us to build high buildings in the United States also, and in Uzbekistan, in any regions. There are a lot of research, quartz and glasses. And he wanted to work with you and as a partner to do projects, to find and to excavate all the resources there, and prolong or do a lot of works with you. And have you heard about this information?
No, I haven't, but I'd be happy to work on that. It looks like a very interesting and challenging project. And if we have a number of people here that have a different expertise, and if we need a different expertise, I can contact people here to help with that process as well. So I will welcome the opportunity to work with you on addressing problems. Absolutely, yes.
Is it visible? Is it visible? This kind of it's a glass which is exported in our region. And what is it? It's a material which is exported there too. And all these materials has 99% of quartz. Yes?
Oh.
We are eagerly want to work with you, and we are looking forward to work with you. And so thanks for you and for organizers Jamshid and Rustam Ishniyazov. Very good and very well organized conference, and we eagerly want to take informations, a lot of informations like this. Seldom. Thanks to your attention.
Thank you very much, and I would be I will follow up through Rostam and Jamshid to continue our discussion, and whatever I can help with, I'll be very happy to help. I would love to. When I was a child, I've heard a lot about Tashkent and Samarkand and Bukhara, and I learned poems with those. So I love to learn more about Uzbekistan and work with you, and I appreciate that. Thank you.
Thank you.
Thank you. So, any other questions?
Thank you. Thank you. Thank you.
Thank
you. Thank you.
Good morning, dear teachers. My name is Victor. So I studied my master's degree in the Polytechnic Institute. So I think today's topic is very relevant, and because construction is carried out every day and everywhere, and we cannot imagine construction without concrete. So, Mr. Professor, how do you think near future can we abandon the concrete? If we can, which kind of material can use instead of it?
How do we get abandon concrete? You said, or not use concrete?
About abandon the concrete.
Oh, abandoned, right? You said,
yeah.
The only well, the idea is not to. It's the biggest man-made material in the world. Concrete is by far whatever material you take is the most. So it's not possible to short-term try to abandon its use. We just have to modify it to make it more environment friendly, to make it more suitable, less environmental impact. However, there are other types of concrete that don't use Portland cement. Now, there is a lot of research on that being done. One is geopolymer concrete or alkali activated concrete, which uses a completely different process in making concrete. And if you are interested in that, I can share some information with you about that. But that uses alkali liquids. It needs silica and alumina in terms of filler materials, maybe some of the pozzolans, and you can make concrete that's as strong as Portland cement concrete. There's a lot of work done in Australia on that, in the United States as well. You can find information about that either under geopolymer concrete or alkali activated concrete. And that's another thing. But those are, again, not going to take the place of concrete. We just have to make the concrete better by reducing its environmental impact and take steps to each time improve that further and further until we have less, because society needs to advance, society needs to improve, and with concrete is a way to build infrastructure, to improve people's lives. It cannot be discarded like that, but we have to try to improve that through research. Okay. Thank you.
Thank you so much. Thank you, Professor Tabatabai, for such an interesting lecture. And you see a lot of questions from, actually today we had students from Karakalpak State University, Jizak Political Institute, I see here Hawaii, Nukus branch of Hawaii Mining Institute and other participants. Actually, I see a provost of Nukus branch, Professor Danyar Juma Muratov. I see Professor Toribek Zakov. Also, I see Salahuddin Akada from Jazak. So thank you, all of you colleagues. You have to understand, it's you have to know about our time difference, because here in Milwaukee it's already midnight. So thank you not only for lecture and also for your time. So thank you.
Sorry that interrupting you. I have only one question to Mr. Dr. Tabatabai. So long time I'm going to ask so high experienced professor about this question. Mr. Tabatabai, thank you for your information and for your presentation. It was so interesting. And my question about it, that you have mentioned about the type of reinforcement, for example, fiberglass or carbon glass reinforcement. My question is usually, for example, steel reinforcement is a joint with the concrete joinable, but the polymer reinforcement is not friendship with the concrete. How do you think if we use, for example, for column, this kind of reinforcement, it's okay or not? I'm going to ask about that.
Yeah, so yeah, it has been a lot of research already done on that. For bars in concrete, they actually create a little, the steel reinforcing bar has protrusions on the surface to improve bond. They actually create something like that for those bars as well. So I don't know if I can go back, but you can see in the picture that I showed that they wrap with a wire, and that creates little dimples on the surface.
Yes, I know it, but surface is smooth. That's why I'm asking.
They actually also sometimes they add little sand grits, little sandy, to make it rough surface. In the bottom of the picture, in the epoxy they put some grits, and so it's a rough surface and not a smooth surface. However, this would work in normal temperatures, but if there is a fire, then the epoxy would become soft, and then you lose bond. So that's still a big problem with FRP with fire, and that could have. But in terms of normal temperature, that with the treatments, it's not as good a bond. So the bond calculations that you do, you have to put the factor, it's higher for those because it takes a longer distance to develop the bond, but still can be done. But in fire, that's still an issue. Okay.
Yes.
Thanks for your question.
Thank you a lot.
Okay. Thank you. That's all. Or Dr. Tabata, you did a good, very interesting lecture. Yes, so a lot of questions we have.
Yeah.
Thank you. It's really my pleasure, and it's thanks to you, Jamshid and Rustam, to make this possible. And I'm very happy for that. If there are any other questions, you can send them to Rustam and Jamshid. They can forward to me, or you can email me directly. I'll be happy to answer any questions, and I'm happy to start discussions about solving problems. And thanks again for the opportunity. It's my honor to make this presentation tonight. And thank you very much.
Thank you.
Rahmet hammaga. Rustam aka ko'rishgancha.
Hammaga rahmat.
Rahmet, onda jumaqlaymiz, vaqtimiz shamol ostida.
Okay.
Jamshid, rahmat.
Thank you. Thank you, Dr. Tababa. So,
xursandman, sizni davom etay.
Juda ham yaxshi. Xudo xolasa O'zbekistonda ko'rishamiz.
Okay.
Mayli, shu bilan konferensiyamiz tugadi. Shu bilan uchrashamiz.
Rahmat.
Rahmat.